Hello students, today we'll talk about Hall effect. So what is Hall effect? Here is the definition. When a metal or a semiconductor carrying a current I is placed in a transverse magnetic field B. So when we place a specimen of metal or a semiconductor which is carrying a current I in a transverse magnetic field B, then what happens is a potential difference is produced in the direction normal to both the current and the magnetic field. So here potential difference will produce in the direction normal to current and magnetic field both. So we'll have three directions. One is for potential difference, second is for current, and third is for magnetic field in X, Y, and Z, three directions, right? This phenomena is called Hall effect. So this is Hall effect. Now what is the importance of Hall effect and why do we use Hall effect? So we use Hall effect to determine a few things about the specimen. First thing is sign of charge carriers. Either it is positive or negative, which means charge carriers are holes or electrons in the specimen. So in other words, we can say that we can find out the type of semiconductor. Either it is N-type or P-type with the help of Hall effect, right? Next thing is charge carriers concentration. So we can find out sign of charge carriers and then concentration as well with the help of Hall effect. And one more thing which is mobility of charge carriers. As we know that mobility of charge carriers for holes and electrons it is different. So we can find out that as well. Now we'll derive a relation which is based on Hall effect. For that we'll consider this diagram. So here let's consider a semiconductor specimen. Suppose this is a semiconductor specimen and this specimen carrying a current I. This is I and it is in positive X direction and the semiconductor specimen is placed in magnetic field B. This is the magnetic field and this is its direction towards Z axis and this creates a force, right? And that force will be exerted on charge carriers. So charge carriers can be holes or electrons and the direction of that force will be towards negative y direction, so downwards. Here this is phase 1, this is phase 2. Suppose we have some charge carriers here, electrons or holes, so uh, these charge carriers will start moving towards phase 1 from phase 2. Now, if the charge carriers are electrons, then what will happen is phase 1 will have more number of electrons because electrons are moving towards phase 1 from phase 2. So phase 1 will have more number of electrons and it will acquire negative charge. So a phase 1 will become negatively charged as compared to phase 2 and we'll say that our specimen is N-type semiconductor. And if the charge carriers are holes, phase 1 will acquire positive charge as compared to phase 2 and we'll say that charge our specimen is P-type specimen or P-type semiconductor. Now what will happen is when one of our phase will acquire positive or negative charge, in both cases what will happen is there will be a potential difference between both phases, right? So that potential difference, actually there is one more term for potential difference which is voltage. So that potential difference or voltage is known as Hall voltage here and we'll denote that by V capital H. And with the help of polarity of Hall voltage, either it is positive or negative. So with the help of polarity of Hall voltage, we can determine the type of semiconductor, either it is N-type or P-type. Now, let's start the derivation, and for that, we'll consider the equilibrium condition. And in case of equilibrium, or we'll say at equilibrium, electric field, capital E, we denote electric field by capital E, due to Hall effect, it should exert a force on charge carriers, right? So why electrons or holes, or we can say charge carriers, are moving towards phase 1 from phase 2? Because of that force only. And that force is exerted due to electric field E. So that force should balance the magnetic force, right? So electric force should balance the magnetic force. How would we write it? We'll equate electric force F is equal to QE, and Q is E here, electron. So E, right? And in case of magnetic field, it is BeV. These are the formulae. We have already learned them in year 12. Now, what is E here? Charge on electron, electric field. This is magnetic field, and this is charge on electron again, and this is drift velocity, right? Drift velocity of electrons. Now, there's a relation between electric field voltage and distance between two plates, uh, between which we'll get Hall voltage. So this is the distance, actually distance between phase 1 and phase 2. So this is D. Distance is small d, and we'll consider Hall voltage here is equal to VH by D. So this is a relation. It's a very basic relation. So from here we can write VH is equal to E times D. And because E is equal to BV, because we can cancel E by E here, we can also write in terms of magnetic field, we can write BVD. So we have value of expression of VH in terms of electric field as well as magnetic field. Now we'll talk about current density, and we denote current density by J. So J is equal to current by area per unit area. So I divided by here we can see that D times W, because length times breadth, here we are using these notations D times W. So we'll write this D multiplied by W at the place of area is equal to rho V. This is also a formula for current density in terms of charge density. So rho is charge density here, and V is drift velocity again. So from here we can say that V, drift velocity, is equal to I divided by rho W D, right? So this is drift velocity. Now Hall voltage. What was Hall voltage? It was BV D, right, in terms of magnetic field. So B, V will place the value from here. So I divided by rho W D times D. So we can cancel D by D. So we'll get BI by rho W, which is equal to Hall voltage. So this is the expression of Hall voltage. And in this expression, if we have value of these quantities B, I, rho, and W, we can find out the Hall voltage, or we can also find out the charge density, which is rho. So we can find out the charge density with the help of this formula. If uh, remaining four quantities, value of remaining four quantities we know, then we can easily find out the value of charge density, or we can say rho. Now, uh, 1 by rho. What is 1 by rho? 1 by rho is equal to RH, because we can find out the value of rho from the previous expression. We can easily do 1 by rho and we can find out the value of RH, and RH is known as Hall coefficient. Let me write it, Hall coefficient. So we can find out the value of VH, we can find out the value of RH. This is Hall voltage, this is Hall coefficient. Now let's try to write RH in terms of VH. So there was a relation, let me write it here. VH is equal to BI times BI divided by rho W. So from here we can say that rho is equal to BI by VHW, and because it is 1 by rho here, so we need to invert the value, so VH times W by BI. Now what is this? This is the expression in which we have got RH and VH both, so Hall coefficient and Hall voltage both. So this is the relation we were trying to derive. In some books they write like this: VH is equal to RH BI by W. Both has the same meaning. We can write any one. Now here the sign of RH indicates whether our specimen is N-type or P-type, or whether holes are predominant or electrons are predominant in conduction process. If RH is negative, if RH is negative, then electrons are the predominant charge carriers, and if RH is positive, then holes are the predominant charge carriers. We can also find out electron mobility, right? We have talked about that when we were talking about importance of Hall effect. As we know that mobility is mu. So for mobility of electrons, so when we'll write RH, Hall coefficient with conductivity, sigma is conductivity. So Hall coefficient, when Hall coefficient comes with conductivity, it gives us mobility. So with the help of this formula, we can also find out the mobility of uh, the space or mobility of the charge carriers, right? So this was all about Hall effect. Thank you.